Okay, Stefan, the stage is yours.
Thank you for having me here. I will show you today some news about Linux on System C, and this is combined with a performance bit of an overview. I have a couple of proof points with me where I can go into more detail of what these proof points mean. Especially we were asked about the compression hardware feature a bit, and I can get into great detail even there. As I said, I got some stuff with me. What we do usually with the What's New session is that we give you an overview of the current distributions we are running on Linux on C and what are the supported versions and what the lifetimes of the versions are. Then I will talk a bit about the new hardware stuff on C15. Well, it's not brand new, but it's still kind of new. And then, as I said, I go into more detail of performance, which will hopefully take the most of the time. And then I have a bit of kernel news, but I have stripped that down very much to really very few key things. Distributions, what do we have available today? With the new machine, there has been also a changed set of distributions that we support. That means some of the distributions like /11 is not supported anymore on the new machine. You can find that on the link on that page where you can see the metrics, which distribution we support on which machine type. What's more important is most of the time is the lifetime cycle and the kernels. And what I would like to highlight here is that for quite some time we have with SUSE the way that we change kernel versions with service packs even. For example, that was the case with /12 where we changed from a kernel 3 to a kernel 4. In the past, we stayed on the same kernel version for the whole lifetime of the major distribution version. Same thing holds true for the compiler versions, especially with /15. You can see that we got really quite new compiler versions which you can install. The regular versions, I think even for the /15 is still a GCC 4 compiler, but there are other compilers available up to the latest version of the GCC 9 you can use, which gives you quite a performance boost if you do compile things yourself. Lifetime, regular lifetime of /11 almost has gone by now. There's a long-term service. So the regular supported versions are /12 and /15 as of now. Same thing for Red Hat. Red Hat took a bit longer to change the kernel versions with the updates, but that's the case with RHEL 8 as well, that there are new kernel versions and new updates for Red Hat Enterprise. And there's also a variety of Linux compilers, of GCC compilers available even up to the newest versions, as well as the was the case with SUSE Enterprise as well. RHEL 6 almost run out of lifetime right now, so everybody should at least change to Enterprise Linux 7 or probably Enterprise Linux 8 with the new update versions. This should be also a good option for people to go to. Ubuntu, there's when I look at that, I see that the 2004 version is missing on that one. There's a 2004 version, which is the next stable version you can go to, but there's also some lifetime left for 1604 and 1804. They have a 5 years lifetime guaranteed from SUSE with an option to long-term service support as well. Same with the other distributions, newer GCC versions where the base GCC versions delivered with Ubuntu are even rather newer ones than the SUSE and Red Hat versions. going to C15 and new hardware stuff, which is quite exciting for us. There has been a change in the form factor, which is when you see some of the publications seems to be the most obvious and one of the important factors that we can fit into a usual standard 19-inch rack, which most other or all other hardware vendors are using. So we are now using that one as well and can fit into a slot that has formerly been used from an x86 system or some other vendor system. There is some hardware news. The most exciting stuff is for us a 14% increase in single thread performance, which we see most all over the board. There are some workloads that have a little bit more and some that are a little bit less, but most of them really have a good benefit from it, and there's a 14% average on that. And what I will also talk later about is that we changed the on-chip and on-core units. We have a new NXU compression unit on the chip, and we have also changed the encryption unit on the chip, made that quite a bit larger, so you can benefit or have a more performance improvement on the encryption facilities. If you would like to use the new system, you have to be on a rather new hardware. That's Red Hat 7.6 or 6.10. SUSE, there you have to, for 12 and 11, have main web updates for it. And for Ubuntu, you have to be at least on the 18.04 long-term service on it. For the Red Hat 8 and /15, they have to be on the update stream, so that still works. It might be the case that things are actually working for you and you can store it and install it, but you might run into problems later. We've seen that with this C13, when I remember it right, it was that there was a problem with the big number of CPUs, which they could run into later. It first looked like running okay, and then it got some problems. So take my advice and update to the recommended levels so that you not run into some strange problems later. CVM hypervisor that we support 7164, and KVM also supports the regular distributions that are right now out there. For the cards, not a lot has changed now, especially what has changed is the form factor of the cards a bit, so that they fit into the new racks, but technology-wise, most of the cards have stayed the same. There's not a lot more features on the cards. All the cards are exploited transparently. There's no support required, so you can just use the regular distributions that are supported on the machine. Now let me just look at that one. The IBM Express 16SA has a improved performance over the 16S card, but is otherwise same as the 16S Plus card. The OSAR cards needs a kernel patch, but not for working. It will work just as it goes. But to show the right card version, hardware version, it will need the name of the card in the code. So there's a patch for that to make that one work. The ROCE Express card, the 2.1 card is a 25 gig Ethernet card or ROCE card. And what needs to be mentioned here, there's no switching to the 10G card it works strictly at the 25G level, and it's not mixable with the 10G cards. Crypto Express card, as I said before, most of the cards overall are in toleration mode right now. So this one is treated as a CAC 6S card and using all the features, has a 6S card as well, except that it's working with a chip and has a performance improvement on that side over the 6S card. A summary of the I/O features. The new ones are the Crypto Express 7S card, the ROCE 2.1 card, and the OSA Express 7S card for the new machine. The Falcon SA card has been there before and has the same performance as the 16S Plus card as well. I would like to mention is that for the OSA Express card, there's a 10 and a 1 gigabit feature available to the 25 gigabit, but as I said, it's not mixable, so it's not going automatically down to the 10 gigabit. The vector instructions have been in there for quite a while, but there's a new version with a new machine. You can see that in the proc CPU info with VXP or VXE2. These are two indicators for a new type of vector instructions, and you need new glibc or a new GCC compiler or LLVM compiler to make use of that one. But keep in mind that things like string, mem are in the library, and you will benefit as soon as you have the new library on the machine. So it's not needed to recompile all of your applications. It just makes use of the new vector instructions by using the new glibc library. One of the new features is a secure boot for SCSI IPL. So that's part of the pervasive encryption effort that we can turn on a secure boot for the machine. So it's checking for mismatches of the kernel image before it's booting that and refuses to boot it if it's tampered with. So now we are getting to the performance stuff, which is a bit more exciting in my mind. We see again the chip of the C15, and on the bottom of the chip you see the NXU compression unit. This is providing hardware acceleration support for GZIP. You can see the 12 cores on the chip, and you can see that we only have one NXU unit on the chip. So this NXU unit, the compression unit, is shared by all the cores on the chip. That also means that the performance of that compression unit has to divide it between those cores. So if you're doing a GZIP on 12 cores, or let's say on 10 cores out of 12 cores, you're doing a GZIP compression, then you get a tenth of the performance of the full compression unit. But since that is very much limited by the I/O you can do, because the compression unit is a lot faster than the I/O you can do to the hard disks, usually that's perfectly enough to really drive 10 compression streams as well without getting to the limits of the compression unit. And I will also be able to use the compression unit at the same time. It's compressing blockwise, and then I will do one block after the other, no matter from which core it comes. So you can have concurrently running compression streams on 2 cores without getting some problems or some contention on the chip. As was promised, we show some proof points for it. So that is what we call a proof point. We do tests, how fast is the hardware running, so we have some idea what could we show to you. And what we have done here is that we took standard files that are used for compression benchmarks and tested those, how much faster they would run if we used the hardware compression on it. This one here is using a regular gzip, not even not real regular gzip program. There's a test gzip program that comes with the libc library, and that one is the one we used for the test. We compiled that one, but did a regular gzip like you would run that one as well, and compared the fastest software version with the hardware version we have, because that's, we think, the fair competition, that you would go for the fastest software algorithm you do have. If you do that, depending on the file size, you get up to a 40 times faster compression using hardware compression. The hardware itself, as I said, is the compression unit is capable of handling 400 times as much as software. It's capable about handling 12 to 15 gigabytes per second, depending on the data you give to it. If it's more random data, it's a little bit less, and it's going even to 7 or 8 gigabits per second. But it's regular data like the Linux kernel, for example, Linux kernel source code, for example, then they go up to 12 to 15 gigabytes per second, which is about 400 times faster than what you can do with software, actually. The reason we only achieve 400 times is that the mini gzip program is having some error. It has to start, it has to check the options you give to it. It has to do the I/O. The test we did with the 15 gigabytes per second was without any I/O. So we put a gigabyte data into the memory and compressed that one and took the result again into memory. So we took great care not to use any I/O in that case. As soon as you do that, it's a lot slower because the I/O is so slow, actually. And I can show you, because that was, yeah, that's the information I gave to you, is a gzip -1, which is the fastest version of the gzip you can do. And that's the one we compare to the hardware compression unit, which is doing a comparable compression ratio to the gzip -1. So it's a bit bigger than the default one for gzip -6. It's about 20% bigger than the default compression you use with gzip. Because on the one side, I/O is a limiting factor, you should take care in which order you do compression and encryption. You would like to compress it and then doing the encryption on it and encrypting less data, and then write less data to the disk as well. The second reason, you really should take great care not to encrypt it before compressing it. When you encrypt it, it's looking like random data, and this is basically not compressible if it's really random, and encrypted data is very close to random, though that's not very good compressible. Though you compress the clear data, encrypt that one, write that one to disk, and benefit from better compressibility and smaller data size when encrypting it. This is a lot of data, but as I said, we were asked some questions about people using the hardware compression and not seeing as much benefit as they would have hoped for. What you see here is a table of the so-called Canterbury corpus, where you have on the left side the file that is used. That's standing for a certain type of data you have, like Alice is a text file, Kennedy.xls is an Excel file. Then we have some in the artificial corpus. We have 1A in a file, have 1,000,000 A or 100,000 A's in a file, and we have 100,000 characters of the alphabet. Then we have random text. Then we have some meaningful text like the E. coli bacteria, the Bible, or some world knowledge, or the digits of pi and so on. And you can see if you have very small file sizes, the hardware speed up factor, which means what hardware compression is faster, how many times hardware compression is faster than software compression, then the speed up factors are rather low. Like fields.c is an 11K file. This is just a bit faster when using hardware. If we use the 1 megabyte Kennedy.exe file, then it's about 10 times faster already. If you go over the E. coli, which are pretty big files actually, then it's cited 30 to 40 times faster, in fact. So these are the ones we cited with our proof point actually. To get a real big file, I put all the Canterbury files into one tar file, which is just concatenated all the files together and then compressed that. And this is the biggest file, so this is giving the biggest speed up. So if we do not see a speed up at all, maybe even, then most likely the reason is that the files are just too small, actually, because there's some overhead in gzip on doing this. Again, this was the base data for the proof point, and this is using the minute gzip program, which is already a bit smaller and has a bit smaller overhead than the real gzip program. There have been some discussions about these things. We do not see any speed up, or the speed up is rather small. So is there any question here about this?
Stefan, no questions so far.
Great.
Go ahead.
Then either it's totally boring or I'm totally clear.
Maybe there's at the end. Let's see.
I have some more. I did some just snoop tests on my system with tar archives for comparing software compression with the default level to software compression with fastest level and the hardware compression actually. Here you can see the numbers I got out of that, and you can also see how I called the tar files, so you can reproduce that one if you want to. So there's the DFLTCC environment variable, which controls if we use hardware compression or not. This is going into the libc library and telling the library, please use hardware compression or not. And there's, for the tar command, you can give the tar command the gzip level you would like to have is gzip equals -6 or -1. So the tar knows to use the level. The hardware compression only works if you specify gzip equals -1. If you say -2, then it will accept the default TCC parameter, but not use any hardware compression because it's working at level 2, and that's only available in software. What you can see here is that if you go from the default -6 to the fastest -1, you already get a factor of 2, about a factor of 2 increase in performance, of course, because that's the fastest level, and this is faster than going for the default. It's twice as fast, and it's 20% bigger a file if you end up with it. If you go to hardware compression, it's even over the fastest, even about 20 times, in this case, 19 times faster than the software version. What you can see at the bottom is there's this real user and system, and the user time would account for the compression level, while the system is kind of doing the I/O in the backend. Yeah? And you can see here that the real time is very close to what you use for the I/O. So the stuff you use for user is either done in parallel, or it's or to the sys stuff in parallel, or it's not taking any time up at all. And this one, let me just look at, yeah. We will see later that we got cases where the compression time you use for that in the hardware case disappears. It's just not something you have to take care about because that's compared to everything else you do. It's a very, very small time the processor uses for the compression unit. I talked about the file sizes. If you take a Linux kernel, I took in that case a 5.0.20, but you can take any other Linux kernel version as well and get very similar numbers to that. If you go for hardware compression, file is about 200 megabytes big. If we go for software compression, default it's about 168 megabytes big. So this is 19% smaller. But still, if you go for the fastest software compression, it's 210 megabytes big. This is a little bit bigger than the hardware compression. The reason for that one is that the block size is a bit different, and that we have more or less headers in one or the other, and so the sizes are not exactly the same for both. If you go for GZIP-1, but you need to remember it's about 20% bigger if we go for the fastest compression, and that holds true for hardware and software. So that's not something specific to the hardware compression we have enabled. There's one funny thing I did. When you go for a tar of the Linux source version, which is mostly the stuff you do, you can tar this big directory, and you either compress it or don't compress it. And what I did here, I compared a no compression case, which is the same in hardware and software, of course, and I did a case with compression using the hardware compression. To get the I/O out of the picture, I wrote the result to def null. That is not going to disk. So if this would be going to disk, you will not see anything of this. It's just the time that it needs when it's been written to disk. The reading from disk does not, if you do it twice, does not take time, because the second time it's in memory cached. So that's also out of the picture here. We are just using the block device subsystem for getting the stuff out of the cache. So there is some I/O going into the kernel, but not real I/O going out to the disk. And what you can see here is if we use the compression, this is even faster with compression than without compression, even that we are doing basically more work to do that. The reason is that writing it later out, reading is the same, but writing it later out is less data. So writing it def null is doing it less blocks, so that's the time it saves. And it saves here more time than it would use for the hardware compression, in fact. So that's one of my favorites, because that's one of the most impressive things that you can really save time by doing more. I did also the gzip case, so that we have some comparison. What is the gzip really doing? Not the mini gzip and these things. So this is really the gzip, and if you use the gzip for it, it's about 24 times faster than using the gzip-1 hardware compression, and that mean in the end it's about 50 times faster than the default compression you're using on Linux. And in that case, I even wrote it to disk in the end. So that's even using the I/O. CPACF.
Before you get to CPACF, Stefan, there was a question if you have any comparison between the on-chip ZEDC versus the old physical ZEDC cards. Any idea how that compares?
No, I can't remember. There was on Share,
okay.
There was a presentation from the COS guys.
Okay.
And I remember that it is faster because you are not having the problem that you have to ship out the data from the memory to the card and getting it back.
Yeah.
so that it'd be a lot faster, because the compression unit, even if it's not on the core but on the chip, it has direct access to the cache levels and does not have to go to the memory out. The card would have to go to the memory, or at least to the level 4 cache.
But what I think what we can say is that the ZEDC, which is on chip now, is faster than the cards.
Yeah, it's definitely faster, but I cannot say how much faster.
Okay.
But I remember that we didn't really want to use it in Linux, and I'm not sure if we did ever some tests on it, how fast it really is, so we do not have any numbers to compare it. But I think it was not something that was really faster than the software compression, because of the problem that you have to get out the data to the card.
Thank you.
This only makes sense if you have really gigabytes of data.
Mm-hmm. Thank you. Go
on. Coprocessor with crypto functions. There has been, I was a little bit irritated, but there's still this copy unit down there on the C15 processor, where we before that had the coprocessor function, all the coprocessor crypto functions located into it. There is still crypto functions in that one, but there's a new unit on the upper right side of the core, the MA unit, which helps us for new crypto algorithms you can use. And that gave us quite some speed up, where we have also taken some proof points for it, where we can see what things are really better. As I said, there's this MA unit is especially enabling this elliptic curve cryptography algorithms, which are coming up quite a lot right now. So this makes really a lot of sense for customers to take a look into, because these are probably the required crypto algorithms for the future. So we are preparing kind of for this stuff. This is not really widely used right now, but it's gonna come up. And what we can see here is that if we take for one of the crypto algorithms, the ECDSE, which is one of the elliptic curve algorithms, we can get 20 times more key exchanges using the new hardware support on the new chip. So that is quite impressive, and all the others are kind of in that ballpark. It's I remember it right, it's all double-digit times faster with the new hardware support, which is kind of the same that we did for the compression. Of course, hardware is most of the time it's incredibly fast, because it's not running an algorithms and kind of instructions through, because it's just implementing an algorithm in a circuit design, which is a very big difference. For key signing operations, we have almost 40 times faster operations with the new hardware support. And I got one more. As I said, all of them are 10 times double digits. It's 10 times more verify operations for the hardware supported operations. All this stuff, of course, depends heavily on how much of the algorithm you can do in hardware, and which parts of the algorithm you still have to do in software. So that's kind of the point where it depends on the algorithm, how much speed up you can see in the cases. I got one more, which is not really CVM centric. It's a KVM centric. We got a new function for KVM. We can load encrypted KVM guest images. These guest images are signed and encrypted on the disk, and they are loaded by firmware, and they are verified by firmware. And the hypervisor itself, without firmware help, cannot load that and cannot log into the guest images. So if you have an operator, an evil operator who's has access to the KVM hypervisor, he does not have to the access to the guest image, and does also not have access to the running guest image inside the KVM. So this guest image is at rest and while running protected from the KVM hypervisor, and that's what we call a secure execution for Linux. And what was pretty interesting for us is such a feature, how much impact does that have on performance? So the question is, how much slower does it run when you enable it with secure execution? And we were kind of afraid that it's really a lot slower, of course, because it's doing a lot of encryption and decryption, and even while running on it. So you have some overhead. And what we've seen here is that you have a 6% CPU overhead. So it's running about 6% slower, depending on the workload, of course, that you have. So 6% of the CPU you have will be needed for the secure execution. In that case, when you have an Nginx web server running on the KVM guests. And there's come up another question that we had. There's the benchmark setup in case you're interested in that. How many bytes we transferred and stuff, and on what system we did run that. But there's another interesting question that came up is this a problem when you have 2 of them running, probably, or 1,000 of them running? And that's also a test we did, that we can have a web page serving workload running on 1,500 guests concurrently on the same box with secure execution enabled, and this at least still does work. I do not have numbers how fast this is working, but as you all know, that all these scaling tests up to 1,500, 15,000, 2 million guests are usually not meant to show that you can scale or can do really considerable workload in that amount of guests. But you can start them, they are working and they are running and they are serving web pages after all. So this is still doing something. I have some kernel news in the end. We have implemented a tag legend for that. You've probably seen that before. The last couple of times I did the What's New for Linux, it appeared that only the supported environment, LPAR, CVM, and KVM bubbles are coming into play. But in case you should see that on others, it shows you in which distribution version that has gone into, or for the support environments, for which environments is this specific Linux feature a benefit. So as you can see here, for all the systems, the kernel space layout randomization is a benefit that we have implemented. So every time we come up with a new boot, the kernel address space does look different. So if you have a exploit implemented for accessing some kernel functions, this will not work after a boot anymore without changing the exploit. So this is a security feature we've put into so that it cannot randomly jump into some kernel functions if you could somehow manage to do this. We've added some CPU measurement facility counters, so you can look into those with LSCPUMF, and you connect those as well with the perf profiling tool if you would like to do so. Then we changed something for the DESDs. This is something we as well, I think as well, customers are asking for. We realized that it's bigger disks. The DESD format takes quite a long time. It even tells you to get a coffee before something else is going on here. And so we implemented a quick mode, which is only formatting the beginning of the disks and doing the rest of the formatting when the tracks are used, after all. This significantly, of course, speeds up the formatting process, so there's no time to get a coffee anymore. But the downside of this is because the tracks have to be formatted at some time. When you do the first write on the track, it still has to be formatted, and that is done at that time then. Other packages we've updated, which are very important packages, is the S390 tools, which holds all the user-space tools and the device drivers. There's the SMC tools for networking, shared memory communications networking, which we have updated. And there's the QClip, which is support for this C containerization environment, which has also been updated. These tools are, of course, are put into the distributions as well, but they are not as regularly updated with the distributions as well. So it makes sense to get those tools separately from the distribution stream and update those to get new functions into it, like the new DASD format comes with the new tools. I'm at the end of my presentation. I think I'm also at the end of my time I've allocated here. I have to thank others because this stuff is, of course, never done by myself. This is a team that's doing those presentations regularly. So I got stuff from Mark Bayerle, Stefan Raspel, and especially the secure execution proof point from Dominic Röhm and the systems performance team that's doing the System C hardware performance evaluations. So I have to really thank those that I can use the data and the charts most of the time. I've shown you the distributions and what the port is looking like and what distribution versions are current right now. I've shown you some new C15 functions like the Accelerator, the compression unit for Linux, and IBM Secure Execution for Linux, and a very limited, admittedly, number of kernel news. In case you should have more interested in that stuff or get documentation on that, there's lots of information out there in the internet. There's blogs that we've implemented where we put also new performance information out in the field, so you can get it before we present it at some conference. And of course, you can ask me questions anytime if you want to. You can, on the lower right side, find a QR version of my vCard where you can read that into your smartphone and have the information like email, telephone readily available. I thank you for your attention, and I'm ready to take more questions if you have some.
Okay, thank you very much, Stefan. If there are any additional questions, post them now or unmute and ask them. It seems that we don't have any additional questions right now, Stefan. So thanks a lot for your presentation. Great presentation. I see the comments here. Thanks for showing us the news of Linux on Z. And with that, I will stop the recording and we will have a short break, and the next session will start at the top of the hour. Thanks, Stefan.